Hello everybody and welcome to this Matlab tutorial. Today I'm going to show you how to visualize spatial feature selectivity of the cortical surface. My name is Felix Schneider. I'm a PhD student here in the Auditory Cognition group at Newcastle University. The data I'm showing today is cortical multi-unit activity that I've recorded in the auditory cortex in response to pure sinusoidal tones. I'm sure most of you have seen maps like this, where you have a spatial feature plotted as a function of cortical distance. For example, here I'm showing you the average best frequency in AP, so anterior, posterior and mediolateral direction. And I'm sure many of you will know that the auditory cortex is tonotopically organized, which means that theoretically adjacent neurons code for adjacent frequencies. And this is what you can see here. On average, the frequency selectivity changes from selectivity to high tones, shown here in blue, towards frequency selectivity to low tones, shown in red, and back. So we see a nice tonotopic gradient from the posterior medial part of the auditory cortex towards the anterolateral part of the auditory cortex. On the right hand side, I'm basically showing you the same plot again, but this time I'm not averaging over contacts. This time I'm showing you the best frequency for each individual electrode. And you can see that there is quite a lot of variability among the best frequencies that I've plotted here, but on average the raw data actually supports the trend you are seeing here on the left hand side. The plot below shows you a similar map. It's from the same animal, but in this case I'm showing you the peak latency, so the time with respect to stimulus onset where the maximum neuronal response was observed. And on this map you can see that the average latency in the posterior medial part of the auditory cortex is shorter and gradually ramps up towards the anterior parts of the auditory cortex. The concept is the same, and you can apply this for each feature dimension or for each functional response property that you like. So what do you need to produce a plot like this? Well, you need the feature selectivity for each individual neuron that you have recorded. Here I'm showing the response of an example multi-unit to different pure tones. I've presented 14 sinusoidal tones, which you can see here. Each of the individual subplots corresponds to a sinusoidal tone that I've presented. And I've presented those tones at 3 different sound intensities, which are color-coded: blue for 50 decibel SPL, black for 60 decibel, and red for 70 decibel. I'm showing raster plots on top, which show the individual spiking response of that neuron to the different stimulus combinations. And each of those points corresponds to a single action potential. Each row corresponds to a single trial. The raw spiking response is averaged in those spike density functions below here. And you can clearly see that we get the highest response for around 4 kHz. And that means we're assigning the best frequency to this particular stimulus. So again, the best frequency is assigned to this stimulus, or to the frequency that elicits the maximum neuronal response, which in this case is clearly this frequency over here. If you're interested how to produce a plot like this, please check out my video on how to produce raster plots, spike density functions, and PSTHs. I've linked that below in the description. Okay, so now I'm going to show you how to extract 2 features, the best frequency and the peak latency, for an example neuron. And I have a cell array over here with the dimensions 3 × 14 that corresponds to 3 sound intensities and 14 frequencies that we've presented. And this cell array initially contained all of the trials for each of the stimulus combinations, frequency times intensity, but I've already averaged over trials. We're now left with an average vector for each of the stimulus combinations. And we can arbitrarily pick one of those combinations and just plot that. And this is what we get. So we have the stimulus onset at time bin 200. Everything before that is baseline activity. It fluctuates a bit, but is more or less flat. After the time bin 200, when we present the tone for the subsequent 200 time bins, we see nice stimulus evoked activity. Okay, so we're gonna start and extract the best frequency for that particular example cell first. So we're now gonna loop through each intensity frequency combination and we're gonna extract the mean firing rate for the first 100 milliseconds. So again, we are interested in this period over here and the mean firing rate in this particular time window. You can also use just the maximum firing rate, but I always found that just the maximum, just a single value can vary quite a lot and gives me maps that are more messy. So by taking the mean, I basically integrate over a longer time window, which gives me more reliable responses. But that's only one way you can do it any other way. Alright, so let's loop through this array. And then we get a single value for each of the intensity frequency combinations. So let's visualize that. And here we see our receptive field. Number 1 is the loudest condition, number 3 is the quietest condition, and we have low frequencies on the left side and high frequencies on the right side, and the color code corresponds to the response intensity. So brighter colors correspond to higher stimulus evoked activity. And you can clearly see we have an area where this cell quite vigorously responds. Let's have a look at the color code, and yeah, so it's a multi-unit. We see firing rates of about 250 Hertz in this region over here, which can be expected, which is quite a good response actually. So the next thing I'm doing is to average across sound intensities. We then transform our two-dimensional receptive field into a one-dimensional tuning curve. And let's have a look at our tuning curve. Yeah, that looks quite messy. So we again have frequency on the x-axis, low frequencies on the left, high frequencies on the right, and the y-axis now corresponds to firing rate. We can clearly see varying selectivity to different frequencies, but yeah, it's quite messy. So what I'm doing next is to fit a smoothing spline to those data and to extract the best frequency based on the smooth curve. Let's have a look at the smooth curve. You can clearly see we get a smoother response curve shown here in red. Now blue is the original data, red is now the smooth curve, and now we can assign the best frequency with more confidence. So we are just looking for the maximum here, and yeah, seeing that the maximum is actually at frequency 7, and we are then just looking into our pure tone array where I've stored all the frequencies and find out that frequency 7 corresponds to 1140 Hertz, which is then our best frequency. Okay, so we have extracted the best frequency. Now let's have a look on how to extract the latency data. Okay, let's go back to our example response. Now latency can be defined in different ways. You can either just look for the time point of your maximum response, which would be defined as the peak latency, or you can have a slightly more complicated approach where you, for example, have a sliding window that you move along your response and you define the first time point where your response gets significantly different from the baseline period, and you would assign that time point as the onset response of the neuron. For this video, we're just going to use the peak latency, but let me know in the comments if you're interested to learn how to determine onset latencies or how to determine whether your response is actually different from the baseline period. So in order to extract the peak latency, we need to do the exact same thing we've done for the best frequency, and that is to loop through each of the different stimulus combinations, and we're going to then find the time point or the time bin of the maximum response during our stimulus presentation period, and we're going to assign this value to the variable pk, short for peak. So let's do that. What we are doing next is we are only extracting the latencies for our best frequency. which you can see here. So these are the three intensities, and we are then also averaging across intensities and getting a peak latency of 53 milliseconds after stimulus onset. Okay, so we have now extracted our two functional parameters for this example neuron. We have extracted the best frequency, and we've also extracted the latency in response to best frequency tones. Now it's time to assign those functional parameters to the actual 2D map of the cortical surface. In order to do that, you need the coordinates of your electrode. Let's assume we have these coordinates over here. Maybe the first one corresponds to the coordinate in anterior-posterior direction, and the second one could correspond to the mediolateral extent. How you define your coordinates really depends on your experimental setup. If you're recording with a grid system, then it's quite easy. You can use the different grid holes and simply count where you are. If you're not using a grid, then you need a different point of reference. The only thing that's really important is that you're being consistent across recording days. We assign our coordinates for the different dimensions to x and y. We initialize our tonotopic and our latency map, and we then also initialize two arrays that are only filled with NaNs, not a number values. And only a single value that corresponds to our coordinates gets replaced by the best frequency and the peak latency. And as a last step, we then concatenate our already initialized tonotopic map with this none array, which now has one entry. So we can visualize this array now. There's not a single number in here except for this one point. And we now take this map and we concatenate it with our tonotopic map, which at the moment is still empty. We concatenate that in the third dimension, which means we just stack those matrices on top of each other. So right now it's only a two-dimensional array. However, as soon as I stack another one on top, it gets three-dimensional. And now you can already guess what the next step will be. You do the exact same thing for all cells in your population. You stack them on top of each other. Of course, the recording coordinates will vary, and at the end you simply average over the third dimension in order to get your average feature map. Okay, so I would have liked to show you that with real data. Unfortunately, the data I'm working with are not published at the moment, so we're gonna simulate our own little data set. We're gonna initialize our tonotopic map, a variable for best frequency and a variable for the coordinates. We then have just arbitrarily chosen 500 cells. We're gonna loop through each of the cells, and we randomly assign coordinates in x and y direction or in AP and ML direction. Based on the coordinates, we also randomly assign the best frequency, and of course we want to show some kind of gradient because the auditory cortex is tonotopically organized. That means the further you go in one direction, the higher the best frequency becomes. Next, we round our coordinates in order to fit them into a grid system. We then again initialize our none array, only replace a single value with our best frequency, and then stack each of those matrices, i.e. we stack the selectivity for each of the recorded, in this case simulated cells, on top of each other. So let's do that. Let's have a look at the size of this array. Yep, it's 18 by 18 by 500. So for 500 simulated cells, we now got the feature selectivity array, and we can now visualize the mean of this map. We just average over the third dimension, and this is how it looks like. You can clearly see that we get a low frequency area over here and a higher frequency selective area over here, but it's still a bit messy. What you can do to get a smoother map is to smooth your map with a Gaussian kernel. So that's what I'm doing here. I'm simply defining the width and the standard deviation of this Gaussian here, and then I'm creating the actual filter. So this function here only considers values that are actually filled in. You can get that function from the Matlab file exchange. It's not built in. So we can then filter our map. And what you see is that your map is a lot smoother now. And then you can also change the color map in order to make it look nicer, and voila, you get a nice simulated tonotopic gradient, similar to the one I've shown you before in the introduction. Alrighty, so we have plotted our average map, and now it's time to look at the individual data points. For that, we again create a figure window over here. We fill the background and just make it black. Unfortunately, we have stored the coordinates of all of our simulated data over here. So we have our x coordinate and our y coordinate, and we can then extract unique combinations of those coordinates and store them in the variable c. Since we want to visualize our individual data points as circles, we need to define the radius of the circle. We need to actually define the number of data points that our circle has. We want to define the transparency of individual points, and of course we need to create a color map. And as a last step, we get the specific coordinate. We get an index to point us towards the specific data points. We average across all best frequencies at that particular coordinate. We define the color. We plot the actual circle over here. We adjust the transparency, remove the edge colors, and voila, we got our first raw data point plotted in our coordinate system. You can do that for all the simulated data points, and then it looks like this. But you can now compare those two maps. You can clearly see the underlying raw data for the average map, which is great, I think. Okay, so I hope this video has helped you to understand how to extract feature selectivity of your cells. We have done that on the example of best frequency and peak latencies, but of course that's applicable to different stimulus features or functional response properties. You now also know how to display the average population activity of your cortical surface. And in addition to that, I've also shown you how to neatly visualize individual data points that make up your average map. If you have any ideas or suggestions on topics that I could cover in the future, leave me a comment. Thank you so much for watching. Stay safe. I see you in the next video. Bye bye.